Okay, for our question, what we're trying to figure out here is the angle, the minimum angle necessary for this line to come in, refract through here, and then create total internal reflection. And what we're going to have to do is backwards engineer it. So we know that the index of refraction here is 2.0 and 1.0 on the outside. So we can start to predict what angle we need to create that total internal refraction. So our sine of 90 is, or our angle here is going to be the sine of 90, and then our index of refraction is 1 on the outside, and we plug in the inside index of refraction times the sine of this angle, which we'll call phi, and that comes out to 30 degrees. Now that we know that, we know that this angle here is where it exits, and this angle here is where it comes in. We can also continue to reverse engineer it, so we plug it all into Snell's law. We have 2.0 times the sine of 30, our initial phi, which is this value here, and then 1.3, the initial index of refraction, and we get sine of phi, where phi equals 50.3 degrees.
Alright, so once we found these angles of phi, we know that all of these angles here are the same because of parallel geometry. And then right now we can focus on the exiting angle right here if we just use Snell's law, and then Snell's law is just n1 sine theta 1 equals n2 sine theta 2. So then we plug in all the values here, n1 and then the sine of 30, which is what we found previously, equals the second index of refraction, 1.3, and then we're trying to find theta. So then you solve using trig to find 50.3, and then this also validates that all of our angles are correct because they're symmetrical.